Okay, so this is our last lesson, Orbital Dynamics. So Newton understood the possibility of sending objects out into space in the 1600s, which is crazy because they didn't send anyone into space for over 300 years after that. So since Earth is a circle, or a sphere, but a circle in 2D, Newton reasoned that an object launched at high speeds from the top of the hill would fall following Earth's curvature. If the launching speed were high enough, they would continue falling forever and ever, never hitting the surface. And we kind of talked about this before with astronauts, why they float in space. It's because they're falling forever and ever, and Newton figured that out. So the speed that you need to fall forever and ever, never hitting Earth's surface, is called the escape velocity. And this allows you to always escape Earth's surface because you have a big enough x component to your speed. Right, and we talked about it before, how if I shot it, it would follow this path, and then it would go bigger, right? If we zoomed out like this, but if you're going fast enough, you would fall forever and ever and ever and ever, and then you would be in orbit. So here's a video that shows this idea of orbiting, so check it out.
Hey Bob, I've been wondering if the Earth pulls on the moon like it seems to pull on this apple.
But then wouldn't the moon just fall down? How does it go around the Earth?
I don't know. If I throw the apple sideways, it still falls down, but at least it goes partway around the Earth. And if I throw it faster,
It goes farther. So?
if I throw it really fast, it goes really far around. What if I throw it so fast that it goes all the way around?
Do that again!
It's in orbit, just like the moon. It's always falling.
But never falls down.
I wonder if that was Newton's idea. He had powerful ideas.
So in the video, it showed that the girl throwing the apple around the planet, even if you could throw it hard enough, why wouldn't this work on the surface of the Earth? Oops, sorry, I was reading off the other page. So why couldn't you do that on the surface of the Earth? What would be your biggest problem? Well, it would be friction. Right, friction would be your biggest problem. So if you threw it hard enough, air resistance, like you'd be going super fast, you'd have lots of air resistance, it would eventually slow down, and then it would hit the surface. So to do this, you need to be above the Earth's surface, right? And I just want to review these terms so that we know what we're talking about in terms of radius. So if we're talking about different planets, right? The radius of the planet is like this. And then this is the altitude, right? So this is the radius of the planet. But when we're talking about orbital radius, that's like if we're talking about a satellite orbiting around, this is our orbital radius. And this is always r in the formula, right? So we have the radius of the planet, the orbital radius, which is r, and then we have altitude, all of those. Okay, so make sure you know which one is which. So calculate the escape velocity of a space shuttle at an altitude of 200 kilometers above the Earth. Right? So here's the space shuttle out here. So the altitude is from the surface, so it's 200. And I'll add on 3 zeros to put it in meters. So 200,000 meters above the Earth's surface. So we have to factor in this 6.37 times 10 to the 6 as well, because we want to use r. Altitude never goes in any equations. So to find the escape velocity, well, it's going in a circle like that. So what makes it move in a circle? Gravity does. So we're using physics principle number 2 to do this question. And this is mv squared over r. And we could use mg, but we can't actually use mg because we don't know what the acceleration due to gravity is 200 kilometers above the Earth's surface. So what we're going to use is we're going to use G m1 m2 all over r squared. So we talked about things canceling out. So we have our object out here, and we have our planet. It's the object that always cancels out, and the planet is the one that always is left over. So the orbiting object is always the one that's going to cancel out. And we have an r down here and an r down here, so those end up canceling out. So I'm just going to switch screens from there and continue this question because it's a little bit easier to write with my hand and not my mouse. So we have mv squared over r is equal to g m1 m2 all over r squared. So this mass is the mass of our orbiting body. That's what cancels out. And this mass that's left over is the mass of our planet. One of these radiuses cancel out, and we're trying to find this. So to find v, our escape velocity, we just go g, mass of planet, all divided by r, and we have to square root it because our velocity is square rooted. So we have 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Mass of our planet is 5.97 times 10 to the 24 kilograms. And then our radius is going to be our altitude, which is 200,000 meters, plus the radius of the Earth. And we have to square root that. So when we plug all of that into our calculator, my calculator appears to be frozen. Let's try starting that up again. So we will go alpha g times 5.97 times 10 to the 24. And then we divide it by 200. 1, 2, 3, 200,000 plus 6.37 times 10 to the 6. Make sure that's all in brackets. And then we're going to square root our answer. And that's how fast an object orbiting Earth would have to be if it was 200 kilometers above the surface of the Earth. So it's going to be 7.79 times 10 to the 3 meters per second as our answer. Okay, that's how you do it. Okay, so let's do a board question. So give this a go, and I will go through it. Probe orbits Jupiter at a speed of that. Determine the altitude of the probe's orbit. Okay. First thing I'm going to do is I'm just going to open up the data book. And rotate that clockwise. And I need some information on Jupiter. Okay, good. So I got that ready to go. Okay, so it's saying that we have Jupiter, and the probe is orbiting around, and we want to determine the altitude, right? So what we're going to find is we're going to find the orbital radius of this probe, but we need to subtract the radius of Jupiter. Okay, so let's switch our screens. So again, anything that orbits, any orbital dynamics question always starts off like this with physics principle number 2, F equals Fg. They give us a speed. We don't know the acceleration due to gravity here. So the mass of our probe cancels out. We're left with the mass of Jupiter. And then one of our radiuses cancels out. And we're trying to find this radius. So I would move the radius up top and the v squared down below. So we end up with g, mass of Jupiter, all over v squared as our formula. So 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Mass of Jupiter. So let's get our data booklet out and find the mass of Jupiter. So the mass of Jupiter, 1.9 times 10 to the 27. And then the speed that was given in the question was 3 times 10 to the 4 meters per second. And I have to square that. So now I'm ready to type that all in. Alpha G times 1.9 times 10 to the 27 divided by 3 times 10 to the 4 squared. And then that's my R value, right? But I don't want, that's Jupiter, that's our probe. We found this distance here. We only want to find this distance. So we have to subtract the radius of Jupiter. So the radius of Jupiter is 6.98 times 10 to the 7. And then this is what we get as our altitude. So we get 1, 2, 3, 4, 5, 6, 7. 7.10 times 10 to the 7, right? That was 7, 1, 2, 3, 4, 5, 6, 7 meters. Okay, and that's our final answer. Okay. So a term that you need to be familiar with is geosynchronous or geostationary satellite. So satellites can be positioned so that they follow the rotation of Earth, and the period of Earth, the time it takes Earth to rotate, is 24 hours. And this you need to know to do these questions. So that won't be given to you in the question. If it says geosynchronous satellite, the period is 24 hours. So these geosynchronous or geostationary satellites are fixed hovering over one point over Earth, which is really good for TV satellites, right? Because if this is the Earth, this is my house here, and this is my satellite dish, and this is my satellite out in space. Ooh, look at that. It beams that signal right down. So when the Earth rotates and my house is over here later in the day, well, if that satellite didn't stay over that one spot, well, it wouldn't beam down to my house in the same spot. So it needs to be over the same spot at the same time so we don't have to move our satellite dishes. So because of its fixed position above a point on Earth, your TV satellite dish need not move while tuned into one station. So calculate the orbital radius necessary to plant a satellite in geosynchronous orbit above Earth. Okay, so orbiting, we're going to use our Fc equals Fg, our physics principle number 2. That's how we start all of these questions. But because we aren't given a speed and we're not trying to find a speed, we have to use our other formula for Fc. M equals 4 pi squared r all over t squared. And Fg is still this. So before r was on the bottom and r squared was on the bottom and they canceled out, but because they aren't both on the bottom, if I move the r up here, it actually becomes r cubed, right? So we have r cubed t squared. Our mass does cancel out, so the mass of our orbiting body cancels out. So what we're left with is the mass of the planet. Okay, so we are trying to find the orbital radius, so we're trying to find this. So I'll move t squared up top, and then I'll move 4 pi squared down below. So to get rid of a cube, you have to cube root it. So it's going to be 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Mass of the planet is talking about Earth, so 5.97 times 10 to the 24 kilograms. Our period is 24 hours, but it can't be in hours in this formula. It has to be in seconds. So we have to go 3,600 seconds in 1 hour. And we have to square that answer and divide it all by 4 pi squared, and then cube root it when we're all done. So this is kind of the calculator gauntlet on the last lesson. Yeah, this is 4 pi squared that I'm covering up on the bottom there. So let's type this in. We can type this all in one step. So for the top, I'm going to go alpha g times 5.97 times 10 to the 24 times, and then I'm going to start a new bracket for these because I want to go 24 times 3600. Close my bracket, and I just want to square the stuff inside of here, so I put my square outside of that bracket and then finish off my bracket up top. And then I'm going to divide it by 4 pi squared on the bottom, and I get this, and I have to remember to cube root, and to cube root, oops, you can just click on this math button here, and it's the fourth one down. So if you click math 4, it'll cube root it, and then second negative will plug in your last answer, and you get this as your answer. So this is the orbital radius. So 1, 2, 3, 4, 5, 6, 7. So 4.22 times 10 to the 7 meters is the orbital radius. So that's how far away satellites are that are geosynchronous. Okay, so let's do another one. Calculate the period of a satellite that is orbiting Earth at an altitude, 4,500 kilometers. Okay, so my altitude is 4,500. I'm going to add 3 zeros to make it meters, and we have to factor in the radius of the Earth if we want to find R in our formula. So we'll have to think about that when we're doing it. Again, orbital dynamics, anything orbiting starts out like this. Again, they don't give us a speed, and we're not trying to find a speed, so we have to use this formula and this formula. Okay, so we're trying to find a period, so I'll move period squared up top. Well, I'll cancel out the mass of my satellite, move r cubed up there, and then this is the mass of Earth. Yeah, it's talking about Earth, so mass of Earth down there and g down there. Okay, and then we'll have to square root this to finish it off. So we have 4 pi squared. Our radius, so what we have to do is take that 4,500, this is in kilometers, so we'll add 3 zeros. So this is our altitude, and then we'll add on the radius of the Earth, and now it's r. And we have to make sure we cube that, divided by 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared, and then the mass of Earth, 5.97 times 10 to the 24 kilograms. Okay, we are ready to type that in. Oops, don't want to forget to square root it. There's not enough room. There we go. Ready to go. So start my bracket. I'll go 4 pi squared, and then I'll multiply it, open another bracket, 4,500 plus 3 zeros, add it to 6.37 times 10 to the 6, and then to cube it, I can push math 3, and that'll put a cube on there, and then I'll close my bracket. And then on the bottom, we have g times 5.97 times 10 to the 24. And there we go. Cool. That's our answer. And then we have to square root our answer. So we end up getting that. And that's my period. But that's in seconds, right? You'll always get your period in seconds. So that's not going to be an answer. So let's switch it to hours. Like if this is a multiple choice question, hey, can you meet me in 11,284 seconds? Well, let's divide it by 3,600. And then we get, 3.13 hours, which is a much better answer and more likely to be there in your multiple choice. Okay, so that's how we do that one. So board question, final board question of the year, calculate the mass of the sun. That's all that's given. So remember, well, we know the mass of the sun here, so we can't just look there, but we're going to try to calculate it and see if we get close to that answer. So how do we know how to calculate the sun, the mass of the sun? Well, we have the sun, and we know that the Earth orbits the sun like that. How long does it take? 365 days. So 365 days is our period, right? We also know the orbital radius of the Earth. So if we look up the orbital radius of the Earth, it's 1.49 times 10 to the 11. So with those two pieces of information, we can calculate the mass of the sun. So we're going to use m4 pi squared r all over t squared, g m1, m2 all over r squared. Mass of the Earth cancels out because that's our orbiting body, and what we're left with is the mass of the sun, and that's what we're trying to find. So move the r up there to make it r cubed, move the g down below, and we're ready to roll. So 4 pi squared, radius 1.49 times 10 to the 11 meters, cubed, divided by 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. And our period is 365 days, days into hours, so there's 24 hours in one day, and there are 3,600 seconds in 1 hour. So it always needs to be in seconds and meters, and we have to square that. And nothing is square rooted or anything like that, so we're ready to type this into our calculator. Actually, that's a pretty good spot right there. So I'll start my bracket. I'll go 4 pi squared times 1.49 times 10 to the 11. And that radius needs to be cubed, so I'll go math 3, and it'll just cube that because I put it right after it, and it's inside the brackets. So that's my top, and then my bottom, alpha g, times, and I'll start a new bracket, 365 times 24 times 3,600, and I want to square that, and then I want to close my bottom bracket. And I get a mass of the sun, 1.97 times 10 to the 30. We compare it to here, 1.99. The reason that they're a little bit off is because this is rounded. If this was to like 5 sig digs, and then the mass of the Earth, or not, the mass of the Earth wouldn't matter. 365 is also quite rounded. It's like there's leap years in there, so it's 0.2525, something like that. So it's just rounded answers, and that's why we're a little bit off. But that's really good, and we calculated the mass of the sun. So now that we're done Physics 20, I just want you to take a moment to look at what you just did. You calculated the mass of the sun, not given any numbers when we started the year. We started off with V equals D over T, and you're trying to rearrange it. It's like, do I move the T up there? Where does it go? You've come a long way. This has been a really hard semester with school shutting down and having to learn it on your own. And if you've made it this far and you've been somewhat successful, you've done a really great job. And I'm really proud of you guys for all sticking it through to the end. And yeah, I'll see you later. This is your homework, so there's some review if you want to do those, and then this is your Orbital Dynamics homework. So let me know if you have any problems and we can go through any of those. Thanks.